Yes, so hopefully the sound is good. Okay. Yes. So nuclear particle density we were going to see yesterday, but due to some reasons I had to quit the class in between. So we will look at it now. That what is nuclear particle density? Okay. So nuclear particle density, as the name suggests, it is the number of nucleons per meter cube. Okay. Nuclear particle density. Particle means particle. What is your particle? Particle is your nucleons. Okay. Particles are your nucleons. Okay. So nuclear particle density simply means that how many nucleons will be present in a unit volume of the nucleus. Okay. So it is the number of nucleons per unit volume of the nucleus. So it is given as. Now how did this formula come? N is equal to nuclear mass density divided by nuclear mass. How did this come? Okay. So let me tell you. Yesterday we had found out that the density of nucleus is 10 to the power 17 kg per meter cube. Yesterday we had found out this. What is this? This is density of nucleus. Okay. This is density of nucleus. We had found out yesterday. So what does this imply? What does this imply? 10 to the power 17 kg per meter cube is the mass density of nucleus. Okay. It is the mass density of nucleus. It is rough estimate. Okay. It is a rough estimate. It is a rough estimate. So what does this imply? This implies that 1 meter cube of nucleus contains 10 to the power 17 kg of nucleons. Now I know the mass of each nucleon. What is the mass of each nucleon? Mass of each nucleon is equal to 1.67 into 10 to the power minus 27 kg. Okay, this is the mass of each nucleon. So the mass of 10 to the power 17 kg nucleon is, so we will apply basically unitary method. 1.67 into 10 to the power minus 27 kg corresponds to 1 nucleon. Then 10 to the power 17 kg nucleons will correspond to how many? Okay, 10 to the power 17 kg nucleon contain how much number of nucleons? Okay, so we will simply use the formula 10 to the power 17 divided by 1.67 into 10 to the power minus 27. Okay, so what will we get? So you can see from here. Okay, this you have done in the fifth standard too. Okay, fifth standard, in the fifth standard also you have done this. So 10 to the power 17 divided by 1.67 into 10 to the power minus 27. How much does it turn out to be? It turns out to be 10 to the power 44 nucleon per meter cube. Okay, so such huge is the number of nucleons per meter cube, means 1 meter cube of nucleus. Suppose suppose there is a nucleus. Suppose there is a nucleus which has 1 meter side, 1 meter side, 1 meter side. Okay, this cube is formed out of the nucleus. Okay, nuclear material forms a cubes. Then how much nucleons will it contain? It will contain 10 to the power 44 nucleons. Okay, so this is the nuclear particle density. Okay, so hopefully you must have got this, that how did this come? Okay, how did this come? You must have got it. Okay, now you understood this, right? So nucleus, a very small quantum system. Okay, what is nucleus? Nucleus is a very small quantum system, right? Let me take a broader line. Nucleus is a very small quantum system, so we cannot neglect its wave aspect. Okay, you know this very well, that whenever a system is very small, we cannot neglect its wave aspect. I had taught you this in the quantum mechanics. Okay, what did I teach you in the quantum mechanics? I had taught you that whenever a system is small, okay, in quantum mechanics I had taught you that whenever the system is small, okay, whenever the system is small, we cannot neglect the wave aspect. Okay, we cannot neglect wave aspect. I had taught you this. And whenever the system, that means the microscopic system. What does this imply? This implies the microscopic system. Okay, microscopic system. And what about macroscopic system? What about macroscopic? In the macro world, we can ignore the wave aspect. Okay, we can ignore wave aspect. Okay, so nucleus is a very small quantum system, so we cannot neglect its wave aspect. So no sharp boundary, it will have no sharp boundary. Okay, as we cannot neglect the wave aspect of the nucleus, so nucleus will have no sharp boundary, because sharp boundary is for whom is there is sharp boundary? Sharp boundary, sharp boundary is for macroscopic world. Okay, macro world. For macro world, there is sharp boundary, but for micro world there is no sharp boundary. If you have learned the quantum mechanics, then I have taught you all of these things over there. Okay, so I don't think there is any need to further explain this. Okay, so there is no sharp boundary of it, because it is a quantum mechanical system. So nuclear region is the one, so nuclear region is the one where the nuclear wave function psi has an appreciable value. Okay, so how will you define the nuclear region then? Nuclear region is the one where the nuclear wave function psi has an appreciable value. Now I had told you that the wave function psi denotes the square root of probability of finding a particle. Okay, so nuclear region is the one where the nuclear wave function psi, suppose this is the nucleus. Okay, so if we magnify the nucleus, so suppose it looks so big after magnification. So suppose nucleus has various regions. This is region 1, this is region 2, this is region number 3. Okay, so the part where the nuclear wave function, okay, the nuclear wave function psi, where if suppose it has the maximum value here, so that means that the probability of finding proton and neutrons over here will be maximum. Okay, over here will be maximum. Suppose it has the minimum value here, psi value is minimum here, so it will have the minimum, the probability of finding protons and neutrons over here will be minimum. Suppose here it is intermediate, so the probability of finding neutrons and protons over here will be intermediate. Okay, so nuclear region is the one where the nuclear wave function psi has an appreciable value. You can understand this in this way also. Okay, suppose this is my nucleus and I magnify it, it looks so much of big. Okay, it looks so much of big. So I had already told you that no sharp boundary. For drawing purpose, I have drawn the sharp boundary, but there will be in actual no sharp boundary of it. Okay, there will be no sharp boundary of it. And suppose in this nucleus, when I move from here till here, suppose I have some specific wave function psi, but from here onwards the wave function psi starts reducing its value, and from here onwards the wave function psi is almost zero, suppose. Okay, so over here there is not a finite value, over here there is zero value. Okay, it is infinitesimally small value over here. Here the probability of finding neutrons and protons is infinitesimally small. So the nuclear region is this much. Okay, so the nuclear region is this much because over this area this entire region has finite value of finding the probability of protons and neutrons. Okay, so this will be called as your nuclear region. So value of psi, wave function psi, for protons and neutrons, okay, this will be finite over here. This will be finite. Okay. Now, there is one more fact, the proof of which we are not going to learn. But there is one more fact, that electrical radius, okay, electrical radius of the nucleus is approximately equal to the nuclear matter of the radius. Okay, nuclear matter radius of the nucleus, we can say. What does this imply? Okay, see, electrical electrical radius of nucleus, not exactly, but it is approximately equal. Okay, not exactly equal but approximately equal to the mass radius of the nucleus. Okay, what does this mean? This means that suppose the nucleus is like this, and the probability of finding the nucleons in this particular region, means this much region, is suppose finite. Okay, so this is basically probability of finding the nucleons is finite in this region. So what does this mean? That means that the wave function psi has finite value over here. That means the mass of proton and neutron, will be found in this region. Okay. So electrical radius means it is related to the charge radius. Okay, electrical radius means charge radius. So the charge and the mass radius are almost same. If I draw the charge radius, the charge radius will also be something of this kind only. Okay, the charge radius will also overlap with this. Okay, the charge radius, suppose it is shown in blue color, so the charge radius will also overlap with this red region. So the area where there is mass present, mass of proton and neutron present, the area where there is mass of proton and neutron present, in the same area the charge of proton will also be present. Okay, means charge of proton means proton has plus one charge. You all know this, that proton has plus one charge. So almost in the same area where there is almost in the same area where there is the proton charge, means the proton charge will also be found in this region only. Okay, the proton charge will also be concentrated in the same region where there is mass of proton and neutron. Okay, so the electrical radius means the charge distribution of the nucleus is almost equal to the mass distribution of the nucleus. Not exactly equal, but almost they are the same. Okay, in the same area the mass and the charge are concentrated over the same area, the same region. Okay, that's what is meant by this, that electrical radius of the nucleus is equal to nuclear matter radius. That is what is meant by this. Okay, now methods to determine the nuclear size. We are going to learn about the various methods to determine the nuclear size. Okay, so what are the various methods to determine the nuclear size? There are electromagnetic methods. What are electromagnetic methods? Electromagnetic methods are mesonic X-rays, electron scattering, Coulomb energies of mirror nuclei, isotopic shift in line spectra, and nuclear force methods are neutron scattering, alpha decay. Okay, so alpha decay we will learn in quantum mechanics. The other from here till here we are going to learn in this class, in this particular class. From here till here we are going to learn in this particular lecture series. Okay, so electromagnetic methods, as the name suggests, it must be related to uh, electron, or electron like particle. Okay, and magnetic field also. Okay, so let's look at this mesonic X-rays. Okay, So in mesonic X-rays, the probe particle is your meson. Okay. In mesonic X-rays, what is the probe particle? The probe particle. Let me look at this. Okay. So mesonic X-rays experiment. In the mesonic X-rays, we have something called as probe particle. Now, what is a probe particle? It is your projectile. Okay, probe particle is your projectile. Let me write over here. Probe particle. Probe particle is your projectile. Okay, which we are going to bombard. Which we are going to bombard on the nucleus. Okay. So probe particle is basically projectile which we are going to bombard on the nucleus of the atom. So in the mesonic X-rays experiment, we are going to bombard the probe particle which is meson, and this meson may have +1 charge or -1 charge. Okay. So meson may have +1 charge or -1 charge, but suppose if we take the -1 charge meson, okay, -1 charge meson. So what is a -1 charge meson? -1 charge meson is just like an heavy electron. Okay, its mass is 207 times. Its mass is 207 times the mass of electron. Okay, so and what is the difference between electromagnetic methods? What is the difference between electromagnetic methods and nuclear force methods? Okay, what is the difference between the electromagnetic methods and nuclear force methods? This will become clear to you when you keep on watching the classes in sequence. Okay, so it will become clear to you that what is the difference between electromagnetic methods and nuclear force methods. Now, right now I am not going into those, but you will understand the meaning. Okay. See, electromagnetic method means the magnetic force will already be there. Okay, because of on account of the moving charge. Because electro means charge is moving. Okay, electro means it is charged body. Okay, and magnetic means as the charge particle will move, so it will create magnetic field. So electromagnetic methods are related to charge and magnetic field, but nuclear force methods, in the nuclear force methods we are basically trying to bombard neutral particles. Okay, we are basically trying to bombard neutral particles. Okay, so it will become more and more clearer to you. You keep watching the classes. So mesonic X-rays. So a mu minus meson has mass 207 times electron, but charge is same as electron. Okay. So let me write over here mu minus meson. Okay. So it has charge is equal to same as electron. Okay. It has charge same as electron and mass 207 times electron. Okay, mass is 207 times electron and charge is same as electron. So that is what is meant by mu minus meson. So it can be called as heavy electron. Okay, so it can be treated as a heavy electron. Over here it is written that mu minus particle can be treated as a heavy electron. Okay, so mass of meson is equal to 207 times the mass of electron, that is written. More suitable than electron, as due to larger mass it penetrates the nucleus long before it decays or is captured by the nucleus. Okay, so if suppose this is the nucleus, and suppose if I bombard such a tiny particle like electron, then it won't go much inside the nucleus. Okay, it won't go much inside the nucleus. This is suppose electron. So electron won't go much inside the nucleus because it has less mass. So it has less momentum, so it won't go much inside the nucleus. So penetration will be low. Okay, penetration for an electron will be low. But in case of a mu minus meson, okay, the same function it will perform because of -1 charge, but at the same time it has mass 207 times the mass of electron, so it will penetrate much deeper inside the nucleus. Okay, it will penetrate much deeper inside the nucleus, so more suitable than electron in this particular mu meson experiment. In this meson X-ray experiment, this mu minus particle is more suitable than the electron because it will penetrate deep inside the nucleus. So it will penetrate deep inside the nucleus before it decays. Okay, so it will decay later. Electron will decay very early, and mu minus meson will decay very slowly and very late. Okay, so positive pions decay as follows. Okay, so you know this very well that how mu meson interacts. Okay, so meson traversing in a matter lose energy, and when their energies are equal to thermal energies, okay, then mu minus mesons are captured into Bohr-like orbits. Now, what is the meaning of this positive pions decay as follows and all these things? You will come to know. Okay, so look at here. So pi minus is like this. Okay, pi minus is like this. Mu minus plus means this is basically your neutrino. So this is the reaction which undergoes over there. Okay, which is undergone in the nucleus. So first of all, mesons traversing in a matter lose energy when their energies are equal to thermal energies of mu minus mesons are captured into, then mu minus mesons are captured into Bohr-like orbits. Okay, so suppose this is your nucleus, then your mu minus mesons will come over here inside this atom. Okay, your mu minus mesons will come inside this atom, because first of all before going towards the nucleus they will basically first encounter the shells, outer electron cloud. They will first encounter the mesons, mu minus mesons, while traveling will first encounter the outer electron cloud. Okay, so they will be captured in the Bohr-like orbits. Okay, the Bohr-like orbits. For example, the electron has Bohr-like orbits. You must have learnt in the lower classes circular Bohr-like orbits. So the mu minus meson will also be captured in those circular Bohr-like orbits. Okay, for one electron atom, the radius of the and the energy of nth stationary orbit are given as. Okay. Now this definition. Okay, of positive pions, and this will be of use to you later on. Okay, when will this be used I will tell you, but first of all you go ahead with this. Okay, so for one electron the radius of the electron atom, for one electron atom the radius and energy of the nth stationary orbit are given as by Niels Bohr formula, by the formula of Niels Bohr. This is the formula of the Bohr's radius. Okay, so, if I try to find the formula of nth energy state for a nth energy state formula for Bohr-like atom, okay, so it comes out to be like this. Now, as the negative meson, your mu minus meson has mass 207 times the mass of electron, so the radius of mu minus meson is 207 times less. Why the radius will be 207 times less? You only tell me. Because over here, instead of mass of electron, over here in this term, instead of mass of electrons, 207 times mass of electron will be written. And as soon as 207 times mass of electron will be written over here, so this expression will be reduced. How many times? 207 times, because in the denominator 207 divided by will come. Okay, so 200 so less than the electron orbit, so Rn will be 207 times less, and over here in the En value, that is the energy of the nth orbit, over here Me is in the numerator. So instead of Me we will have 207 Me, because mu minus meson has mass 207 times that of electron. So 207 Me will come in the numerator. So Rn will be 207 times the mass, the radius in case of electron, and En means in case of mu minus meson. Okay, this also in case of mu minus meson. So this will be, no, this will be 207 divided by, okay, and this will be 207 times the energy of nth orbit in case of an electron. Okay, so it is like that. So what does this mean? This means that the just like the electron, the what Niels Bohr told, told that the electron is revolving in the circular orbit, okay, quantized circular orbit around the nucleus. Okay, Niels Bohr told that quantized circular orbits are there, Bohr-like orbits, in which the electron is revolving. So similar work is being done now by the mu minus meson. Instead of electron, now the mu minus meson is revolving around the nucleus, okay, in quantized orbits, and the energy of those orbits, the energy and radius of those orbits have the following relations with the radius and energy of the orbits. Okay, so in case of electron, whatever is the value, in case of electrons, whatever is the value of radius and energy, those are on the right hand side, and in case of mu minus meson, what are the values of radius and energy, those are on the left hand side. And those two those two corresponding values have the following relation. By this formula you can clearly see this, okay, with the help of this formula. Okay, because Me will be replaced by 207 Me everywhere in the formula. So as Me will be replaced by 207 Me everywhere in the formula, so radius of the nth orbit in case of electron, radius of the nth orbit in case of electron will be 207 divided by, okay, means this will be divided by 207 times less, and this will be 207 times more, okay. So over here it is written as mu is equal to 207 times mass of electron. So Rn mu minus is 207 times less than the electron orbit. En mu minus is 207 times greater than, over here it is less than, over here it is greater than, 207 times greater than the corresponding bound electron. Okay. The de Broglie wavelength of bound muon is much shorter than the de Broglie wavelength of bound muon. Okay, bound muon is much shorter than the wavelength of a bound electron. Okay, so de Broglie wavelength of bound muon. Bound muon means the muon revolving around the nucleus of the atom. Okay, so de Broglie wavelength of bound muon is much shorter than the wavelength of bound electron. Why? Why? Because lambda is equal to h divided by square root of 2 me. Okay, this you had learnt in the quantum mechanics. Okay, this formula you had learnt. So over here once it will be mass of electron and once it will be mass of muon. Okay, so in case of a muon, the de Broglie wavelength of a muon, okay, de de Broglie de Broglie or de Broglie, whatever you call it, so de Broglie wavelength of a muon, okay, will be less than that of an electron, because muon has greater mass. Okay, because muon has greater mass and it is inversely proportional to mass. Okay, right, the de Broglie wavelength is inversely proportional to mass. From this formula you can clearly see this, h by mv. From this formula also you can see it. Okay, and by this formula also you can see lambda is equal to h divided by square root of 2 me. Okay, so the de Broglie wavelength of bound muon is much shorter than the wavelength of a bound electron. Hence it can be localized more sharply than the electron. So you know this very well that the smaller is a particle. Okay, the smaller is a, now I am telling the meaning of this thing. Hence it can be localized, means muon can be localized more sharply than electron. Okay, muon can be localized more sharply than electron. I am telling the meaning of this. you know this very well that smaller is a particle. Okay, smaller is a particle mass wise. Okay, means smaller in mass. Smaller is a particle mass wise, that implies greater is its wave nature. That implies it is difficult to localize such a particle. Okay, so smaller is the mass, is a particle mass wise. For example, electron, which is smaller in mass than the mu minus muon. Okay, so as the electron, and it means E minus is very much smaller in minus, electron's mass is much smaller than the mu minus meson mass. So it has more wave nature. Electron has more wave nature. So electron will be difficult to localize as compared to mu minus meson. Okay. So it is written over here that mu minus meson can be localized more sharply than electron. As electron is difficult to be localized, so we can say the other way also. Electron is difficult to be localized means mu minus meson can be localized more sharply. Okay, means mu minus meson can be localized more sharply than electron. That's what has been written over there. Okay, so the upcoming sentences are over here. Okay, the upcoming sentences, let me put this above. Okay, okay. So the muon, thus once locked in Bohr orbit, jumps from orbit to orbit, moving closer to the nucleus. Okay, so the muon, after being locked in the Bohr type orbit, will jump from orbit to orbit, moving closer to the nucleus. Okay, it reaches the 2p state in most materials. Okay, so you know that, you know this very well, that the atom has 2p orbital. Okay, you know this very well, na, that the atoms have the following orbitals, right? 1s, then 2s, then 2p, then 3s, then 3p, then 3d. You must have learned this while writing the electronic configuration in chemistry in lower classes. You have learned this in chemistry in lower classes, that 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, this is the order of orbitals. Then 5s, 5p, 5d. Okay, you must have learned all of this in the lower classes. So the over here, as we move from here till here, as we move from here till here, we are going outwards, outwards shell wise. Okay, over here is the nucleus. Okay, nucleus of the atom. So we are moving outwards from it. Okay, so 5d will be the most outward. Okay, then so reaching up to 2p, requires 10 to the power minus 13 seconds. Reaching up to 2p requires 10 to the power minus 13 seconds. That's what has been written over here. Okay, so it reaches the 2p state in most materials in about 10 to the power minus 13 to 10 to the power minus 14 seconds. So it reaches the 2p state in most materials in about 10 to the power minus 13 to 10 to the power minus 14 seconds. After capture, the meson 2p 1s transition with emission of gamma rays. Okay, then 2p to 1s transition occurs. Okay, over here, then 2p to 1s transition will occur. Okay, and when 2p to 1s transition occurs, emission of gamma rays takes place. When 2p to 1s transition occurs, then the emission of gamma rays takes place. Okay, over here it is written gamma rays emission occurs. Okay, with a lifetime of 10 to the power minus 18 seconds. Okay, now what are these half life, lifetime, etc.? Those you are going to learn later on. So where is the mouse? Let me see. Yes, So the X-rays energy were measured. So gamma rays reach over there in the 1s, and gamma rays are emitted after 2p to 1s transition, and lifetime of that is 10 to the power minus 18 second. So after you study the radioactivity, after you study the radioactivity part, you will be comfortable with this. Okay, what is half life, what is lifetime, okay, all these things. The X-rays energy were measured. Okay, the X-rays energy were measured. The experimental measurement of R naught in this experiment is found as, the experimental measurement of R naught is found like this. Okay, so this is what is the experimental measurement of R naught. This is the same R naught. Which R naught? This is the same R naught. Which one? That one. That one. You had learnt R equal to R naught a to the power 1 by 3. Okay. This one. So this is the same R naught. Okay. Over here. So in this way, mu minus meson experiment, the this in this way the value of R naught can be found out. Okay. Now now we will learn about these reactions which have been written over here. Okay, these nuclear reactions which have been written over here, means equations, I would say, rather, instead of nuclear reactions I would say the equations which have been written over here. Okay, so see, uh, you can represent this muon as a pion. Okay, so originally it exists as a pion when you bombard it. Okay, when you bombard it with the help of a cyclotron, it is like a pion. So I had told you that mesons are of two types, mu minus meson and mu plus meson. So mu plus meson will exist in the form of a pi plus pion, and mu minus meson will exist in the form of a pi minus pion, while we are bombarding it with the help of a cyclotron. Okay, when we are bombarding it with the help of a cyclotron, these muons exist in the form of pions. Okay, so mu plus meson will exist in the form of pi plus pion, and mu minus meson will exist in the form of pi minus pion. So this pion pi plus will decompose after going into the atom. Okay, after interaction with the atom it will decompose. Okay, not atom, after it reaches the nucleus. Okay, after it reaches the nucleus it will decompose something like this. Okay, then this mu plus decomposes giving a positron, and these things. Okay, this is neutrino, this is antineutrino. Okay, and a pi minus pion will decompose into a mu minus meson, and it will release a neutrino. So like that. Okay, so after penetration into the nucleus these reactions happen, and mass of pi minus, as I already told you, it is 207 times the mass of electron. Charge is equal to charge of electron. Spin is equal to half. So pi minus behaves as a heavy electron. This I have told you. Okay, so this is the Masonic X-rays experiment. Okay, now we will move on towards the electron scattering experiment. Okay, now we will move on towards the electron scattering experiment, but we will move on towards that in the next class. Electron scattering experiment will be done in the next class. Okay, so let me see how much it is remaining. So this is the electron scattering experiment which we are going to do in the next class. And in the examination, whenever Masonic X-rays experiment is asked, okay, whenever Masonic X-rays experiment is asked in the examination, you have to write this dicto. Okay, just dicto, copy down this and write it as it is. Okay, which thing, this is there in the Telegram group also. These notes are there in the Telegram group also. You can download from there and look at it. That Masonic X-rays, the way over here it is written, you have to write it the same way. Okay, or you can add, make some value additions over there. Okay, so thank you very much. Jai Hind, Jai Bharat.